quick recap of what we've done so far this year. Day one, we learned or reviewed about functions and talked about how important they are because they show relationships between variables in real life. Then we went into an operation called limits of functions, which the main purpose of them, as far as we're concerned, is to get ready to another operation, define another operation called taking the derivative of a function. And the derivative of the function finds the instantaneous rate of change of the dependent variable with respect to the independent variable, or basically gives the slope of the graph at any point. So we did show one example. If the two variables in the function were position and time, when you take the derivative, you get the velocity of whatever is moving. And I'm having you take on my word that there's going to be many more applications when we get into the next chapter. But for this chapter, what we really want to do is to be able to learn how to take the derivatives of as many functions as possible. And what we've already done is use this formula. And again, a quick review of how the formula came from. Here's the function y equals f of x. We take any point x here, and then we go over just a little ways to where x has gotten a little bit bigger. So it's now x plus h. And we take the average rate of change in between the slope of the red dotted line, which we called the secant line, and we kept bringing this point closer and closer, and we saw that the red line got closer and closer to the green line, and it's really, we're looking for the slope of the green line. So the way we got that point closer and closer is to let h approach 0, so that x plus h really just became x, and the 2 points magically become 1. And we find the slope right at this point, and we called it f prime of x. So this red is the slope of the red line, and then when you take the limit, it becomes the slope of the green line, the slope of the tangent line. And now we have a new function f prime of x that gives us the slope of f of x at any point x. Now, we've already worked with a few functions, like we did x squared. We put x squared in for f of x, did a little bit of algebra, and found that it was 2x. Then you could do the same thing with a function that's a straight line function like 5x. We could put it into this formula and it wouldn't be too hard, but we talk like, hey, we can just use our heads. 5x is just a straight line that always has a slope of 5 by definition. Therefore, if it always has a slope of 5 for every x, we could just say f prime of x is 5. No matter what x you put in there, the slope is going to be 5. Now, we haven't done this, but what if f of x was just a horizontal straight line, like f of x is 3? Then, what's the slope at every value of x? It's 0. So we could put it into this derivative formula, but we don't need to. We just know that f prime of x is always going to be 0. So now we've started to form some formulas. And let's just write the ones that we know. The derivative of a function, and this is the way you say you're taking the derivative of some function, and you're trying to write it out as a formula. I'm just saying the derivative with respect to the variable x of any constant function, like this one over here, is always just going to be 0. So that's a nice thing to know. What if I have the derivative of a constant times x? Like in this case here. I know that if this were 6x, the derivative would always be 6. So I can just say The derivative is always what that constant is. So now I've gotten not just two functions that I can take the derivative of, I've got every type of function that's a constant or a constant times x. Okay, let's see if we can go further. We know the derivative of x squared. I wonder what the derivative of x cubed is, of x to the fourth, etc. Well, the trouble is, we could use this formula and do all of those, but it would take a long time, and it gets a lot harder. The algebra gets a lot more difficult. So, this is what mathematicians do. They said, I don't want to do all those different powers of x. I wonder if we can come up with a formula for x to the n, where n is any integer. So, how am I going to do that? Well, this is the only formula that we're ever going to have to find the derivative of a function. So we have to use it. So I'm going to say in this case, f prime of x is the limit as h approaches 0. So we're using this. F of x is x to the n. F of x plus h is going to be x plus h to the n minus x to the n all over h. And now we have to do some algebra. Well, how am I going to take x plus h to the nth power? Well, we can use the binomial theorem. We can say x to the n plus n x to the n minus 1 h to the first power plus n times n minus 1 over 2 factorial times x to the n minus 2 h squared. And then we could go, the next term is going to be n times n minus 1 times n minus 2 over 3 factorial, x to the n minus 3, h cubed. And this keeps going until eventually, that's why you put some dots, we come up with n x to the first power, h to the n minus 1, and then lastly, h to the n. Don't worry, even though it's a nice formula, you're probably not going to need to know this binomial expansion. And what's the last thing? We have to subtract this x to the n and then divide by all of this by h. And you're probably thinking, oh my goodness, what a mess we have. But look what happens. This x to the n here cancels with this x to the n, and then every term that we have here has an h in it. So I can divide this h into every term, and so that h goes away. This becomes, instead of h squared, h to the first power. Every power h goes down by 1. So that's h to the n minus 2, and this is h to the n minus 1. And it still looks a little bit messy, but now look what happens when we take the limit. The limit, as h approaches 0, we just plug 0 in for h. That whole term just drops out. In fact, every term has an h in it. So every term drops out, and we're left with that very simple expression, n x to the n minus 1. And we've got a very powerful formula there. We now can take the derivative of any power of x. And let's see if it works on x squared. In this case, n would be 2. 2x to the first. It seems to work. what do you think the derivative is of x cubed? Easy. 3x squared. This seems to be a very powerful formula. Okay, let's see if we can even go further. What happens if we have a function instead of x cubed? What if it was 4x cubed or 5x cubed? In fact, in general, I wonder what happens if we take the derivative of any function f of x that has a constant in front of it. I wonder what we can do with that constant. Well, we have to go back to this formula. So, what's the derivative of a constant times f of x? We have to say it's the limit as h approaches 0 of c f of x plus h minus c f of x. We're just using this formula, all divided by h. Well, you can see that we can factor out a c. We can factor out a c and just make it f of x plus h minus f of x. And because limits are our friends, they do exactly what we would hope they would do. If you have the limit of a constant times a function, you're allowed to take the constant out front. And we're left with exactly this formula. So we get what? C f prime of x. And we've got a new formula. If we've got a constant in front of a function and we want to take its derivative, we can just take the derivative of the function and then multiply by the constant. Just like we would hope that it would work out. So what's the derivative of 4x cubed? It's going to be the 3x squared times 4. So it's going to be 12x cubed. I'm sorry, I think I did that wrong, sorry. If we have x cubed and we want to take the derivative, it's 3x squared. If we had a 4 in front of that, it's going to be just 4 times 3x squared, or 12x squared. So that's going to be a really powerful formula that we know what to do with constants in front of functions. Well, let's go even further. What if we had to take the derivative of 2x squared plus 3x cubed? What if we have a function plus another function? What if we want to take the derivative of f of x plus g of x? Well, I'm not going to write it again. If I want to take this, I'm going to put the limit as h approaches 0, and now I get f of x plus h plus g of x plus h minus f of x plus g of x all over h. Again, I'm just using this formula, but putting in place of f of x, now I have f of x plus g of x. Now, with a little bit of rearranging, I can break this into two separate terms, and I can put the f of x plus h minus f of x together. So I get f of x plus h minus f of x all over h. and then I have minus, well actually it's plus, g of x plus h minus g of x. I'm just kind of combining these together, and I still have the limit as h approaches 0. Now I'm just going to break it into two separate limits, because the limit of a function plus a function is the limit of the first function plus the limit of the second function. Limits are still our friends, and they always will be. So I can say f of x plus h minus f of x all over h plus, now the limit of this second function, g of x plus h minus g of x all over h. And lo and behold, that is our f prime of x. And this is our, what we could call g prime of x. Because it's the same formula with just g in front of x. So what did we just prove? We proved the derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. Just the way we had hoped it would work out. So if I want to take, if I have a function y equals 2x squared plus 3x, I can just say, I can use these two formulas to say 2 times 2x is 4x, the derivative of this part, and the derivative of 3x from this formula is just 3. There's an example. Oh, sorry, it's not equal to that. This would be your function, so this would be, we would call it dy dx. The derivative of this would be 4x plus 3. This is going to be so helpful. It's making our life so much easier than every time we get a function, we have to go back to this limit formula. And I think you can see without too much trouble that if I put a minus sign in here, the only difference would be all of these would be minus, and there would just be a minus in front of there. I'm going through this fairly quickly, but it would also work just as well with a minus sign there. So if this happened to be minus 3x, then the derivative would be 4x minus 3. So now we've developed some really nice formulas that we're to the point where in this short time that I've just talked to you, we've been going from not having the ability to take many derivatives without a lot of work to now we can take the derivative of any polynomial. So say I say f of x equals 10x to the fourth plus 2x cubed minus 3x squared plus 5x minus 53. If I want to take the derivative of that really complicated looking polynomial, I can just use all our formulas that we've developed. The derivative of x to the fourth is 4x cubed. And we know if we have a constant out front of it, we can just multiply by that constant. So altogether we get 40x cubed. And we know the derivative, if you're adding two things together, we can just take the derivative of one and then add it to the other. So what's the derivative of this one? x cubed, the derivative is 3x squared times that constant at 2 is 6x squared minus the derivative of x squared is 2x to the first, so you multiply by the 3 and you get 6x. Using this formula, the derivative of 5x is 5, and any constant function, we know the derivative is 0. Voila! We've got the derivative of this really complicated function, which I'm sure you're glad you didn't have to use that formula to find the derivative. So, now we can go over to the other board and actually look at an example where we can solve something. If f of x is equal to x to the fourth minus 2x squared plus 2, this polynomial, find any horizontal tangent lines and find out where they exist. So this is a fourth degree polynomial. We're going to look for horizontal tangent lines. I've never used that expression before, but think about it. What is a horizontal tangent line? If you have a function that looks like this, a horizontal tangent line is a place, or occurs at a place, where the slope is going to be straight across. It has a horizontal slope. In other words, a zero slope. So what we're doing is we're looking for where on this function is the slope equal to 0. The way we're going to do it is to take the derivative, because the derivative gives the slope at any point. So now using our formulas, what's the derivative? X to the fourth becomes n x to the n minus 1 minus 2 times 2 is 4x to the first, and the derivative of 2 is just 0. So this gives the derivative or the slope at any point. We're looking for where the slope equals 0. Now it becomes an algebra problem. Well, what can we factor out of here? We can factor out a 4x, and we get x squared minus 1. And we can see that at x equals 1, when x equals 1, when x equals negative 1, and when x equals 0, those are the 3 places on this curve up here where they have a horizontal tangent line. Now, what is the y value? When I plug in 0 to here, I get 2. When I plug in 1, I get 1 minus 2 plus 2, or 1. And because these are even powers of x, I'm going to get the same thing at negative 1. So I know where on my graph, at 0, 2, at 1, 1, those are the 3 places where they exist. Now, what are the actual equations of the tangent lines? The tangent lines look like this. So they're horizontal lines, so they're going to be y equals 2 and y equals 1. They're horizontal tangent lines. They're straight lines with 0 slope. So we've answered the question. Now, I didn't ask you this, but has this given us some knowledge what this graph might look like? I wouldn't be surprised if we have a 0 slope here and a 0 slope at these other 2 points. I would guess that this 4th degree polynomial looks very similar to that. So you can see this is going to help us graph functions when we get to the next chapter. Right now we're just concentrating on being able to do this. So we've got these. I wonder if we can find out 2 more things. our derivatives really going to be our friends? What's the derivative of f of x times g of x? Can we just assume that it's going to be f of x times the derivative of f of x times the derivative of g of x? We can't just assume that. We have to go back to this formula. So I'm going to try it. The limit as h approaches 0 of f of x plus h, g of x plus h, minus f of x, g of x, all over h. What am I going to do next? This is kind of something that you might not just think about, and don't worry about if you wouldn't have thought about it, but I'm going to try something. I'm going to go and take this first term, and then I'm going to wait at the very end and throw that minus f of x, g of x, all divided by h. But in the middle, I'm going to add, let's see, I'm going to add f of x plus h, g of x, and then I'm going to subtract it, and then I'm going to add it back in again. So really, it's making it look more complicated, but all I've done is subtracted and added the same thing, so I really haven't changed its value. I'm still going to have the limit as h approaches 0. I'm just going to take and break this up a little bit. I'm going to make this f of x plus h times, I'm going to factor out the f of x plus h out of these first terms, and I get g of x plus h minus g of x. And over here, I can factor out a g of x, and I've got f of x plus h minus f of x. And all of these things are over h. So someplace in both terms I have to divide by h. And I think if you look back a little bit, you're going to see that this is the same thing as this. But we still have our limit. But we know that the limit of a function plus a function is the limit of the first one plus the limit of the second function, and the limit of this times this, because limits are really our friends, is the limit of the first one times the limit of the second one, and the same thing over here. I can say the limit as h approaches 0 of g of x times the limit as h approaches 0 of f of x plus h minus f of x all over h. Don't worry if this is looking a little complicated. Just try to understand that what I'm doing makes sense. Now, as h approaches 0, that h is going to go away, and this is just f of x. And this is just our formula for the derivative of g. And over here, as h approaches 0, that doesn't even have an h in it, so it's just going to be g of x. And then this is our definition of the derivative of f. Well, with all that work, we've got a definition. The definition f of x times g of x is the first function f of x times the derivative of g of x plus g of x times the derivative of f of x. Unfortunately, derivatives aren't quite as much our friends as limits. We wish the answer had just turned out to be f prime of x times g of prime of x, but unfortunately it doesn't work out that easy. But at least we know how to do it. So, if I had a problem like this, y equals x squared minus 1 times x cubed plus 3x, if I wanted to take its derivative, I could just say it's the first function, f of x, times the derivative of the second function, so that would be 3x squared plus 3 plus the second function, g of x, times the derivative of the first one, which is 2x. And that would be our answer. So a little bit more complicated, but it does give us lots and lots of possibilities that we've never had before to take derivatives of functions. Okay, I think you've seen enough detail here and back when we did the simpler ones over here that I'm not going to do the same thing for the derivative of f of x over g of x. I think you can kind of guess that it's not going to be f prime of x over g prime of x. It just, multiplication and division usually go together. So since it didn't work on multiplication, it's probably not, and sure enough it isn't. I'm just going to give you what would happen if you went through all this with division. It's even a little bit more complicated than this. So what you get is g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared. And it's called the quotient rule. Whereas this one was called the product rule. They actually have names because they don't work exactly the way you would hope they were. You don't have to have a special name for addition because it works just the way we would hope it would. Now, these you just kind of have to memorize. The product rule isn't too bad. This one's a little bit more difficult. So just to give you a way that maybe you can remember this better, in f of x over g of x, if we call the top function high, because it's up high, and the other one low, what does our formula say? It's low times the derivative of high, so low d high minus high d low, meaning derivative of the lower function all over low squared, the bottom function squared. So it's almost like we've got a cheer now. We can go low d high minus high d low over low squared. Now let's go. We've got a cheer that we can use to remember the quotient rule. And let's just try to end the day. Let's take a function, x to the fourth plus 1 over x cubed plus 2x. What would we have to do to take its derivative? F prime of go our cheer. Low x cubed plus 2x times the derivative of high, which is going to be 4x cubed plus 0, minus high, x to the 4th plus 1, d low, which is 3x squared plus 2, all over low squared. And maybe you could do some simplification, but I'm happy with that for an answer if you are. So, we've learned a whole lot today, but we've made so much progress from just being able to take derivatives of functions like x squared. Now we can take all polynomials and we can take products and quotients of functions. And without using the limit formula. We've used the limit formula to come up with all these really powerful formulas. So it'll take some practice, but we have plenty of time to practice these formulas. So, thanks for your patience, and we'll see you the next time.